give me a few details.
Prego Alberto, possiamo cominciare, grazie.
20 minutes? How long?
No, 25.
Plus 5.
Ok, plus 5, thanks. Scusa Alberto.
Ladies and gentlemen, we're going to start our morning session with Alberto Carpentieri. He will talk about what's written on the screen, so I don't need to read it. So he has 30 minutes, 25 to speak and 5 minutes for questions. Alberto, your turn.
Thank you. Thank you, Mr. Chairman. Good morning to everybody. The speech of today is related to our long-term experiments on electrolysis. Just to be precise, we are going to see what occurred in our experiments related to palladium and nickel. We had a series of 4 tests. The first was a preliminary test before the project, and the last 3 were concluded were performed during our project, European project. So in this speech, I will try to emphasize that the phenomena which are characteristic for this kind of experiments are also very well correlated, in some cases extremely well correlated. My co-authors are 2 young colleagues, Francesco Montagnoli, who is a postdoctoral research fellow at the Politecnico di Torino, and the second is Stefano Roggeri, who is a PhD candidate. So just a few words, some short notes on the history of cold fusion, so-called cold fusion. And yes, only the milestones. Milestones means that the first people were, of course, Fleischmann and Pons in 1989, and they emphasized, I think, mainly the heat generation. Then, after some years, about 10 years, Mizuno was the first emphasizing also chemical composition changes and the neutron emissions, more or less correlated. And the last milestone is Mosier-Boss in 2008. We have the 4th phenomenology, which is represented by alpha particle emissions. Yes, I have to say that especially at the beginning of my research in this field, which is now nearly 15 years ago, one of the first things that I observed in the famous book by Stones is that he, in 2 parts of the book, emphasized the existence of, in some way, a 5th phenomenology, which is the fracture, more exactly microcracking. There are the 2 quoted sentences, the most important sentences. They were sections of the book, not 2 sections, but I want to show you 2 key sentences, in my opinion, where he says that there is a critical crack size, or better to say, there are cracks of a critical size, which represent the environment and the location of layers. The second point is that there is also a resonance frequency, which is very important for this kind of phenomena. A frequency which is he doesn't declare establish this crack size or frequency. I think that in our research, I will speak about that maybe better to say I've spoken and presented to you these concepts in other speeches, in other occasions, but you know that I consider the nanoscale for the cracks and the terahertz the key frequency for this phenomena. And they are strictly correlated dimensions. Then we can say that the phenomena that I consider has characteristic, but I can say more, I think very well correlated, are 5 phenomena. So in some way, I will consider at first fracture, better to say micro-cracking and fracture, because it's my major, my field, the field from which I started in my career, also for other problems, of course. In particular, brittle fracture and fatigue, and also fatigue. So there is the point 1, which will be a short section of my speech. Section 2 is about chemical composition changes. Section 3 is about neutron and alpha particle emissions. And section 4, which is the last, not the least, but is represented by heat generation, which is the most important point, I think, for in general is considered the most important point. Yes, no, I would like to add, excuse me, I would like to add, I think, just closing this introductory part, very important for me to say that I try to have always, we can say, multidisciplinary research. In fact, you could, in some way, you can substitute the first section with the words microbubble, implosion, and cavitation. And then you have all these consequences, the same consequences. This is also part of my research, but I will not speak about that today. Then, very important, the point from which I started is crashing. It means failure in compression, crashing of iron-rich and calcium-rich natural rocks. Very, very important to say that in this case, we have not the fourth point, I mean heat generation. So up to today, at least, it's not possible to obtain energy from the crashing or rupture of materials. We cannot exclude, I can say, but there are not thermal evidences. Excuse me. No, yes. Yes, this is a panoramic view of our setup. First of all, there are neutron detector, we can say the helium-3 neutron detector or counter, which has 2 parts. The first is the control unit, and the second is this tube for the detection. Then we have the cell, the electrolysis cell, and in the bottom part you can observe also the thermocamera, which is essential to have our results related to calorimetry, of course. This is a particular of the cell. You can see his structure is not a large object, of course. There are 2 electrodes, palladium and nickel. The length is about 4 centimeters, and the diameter is 3 millimeters. Then they were immersed, of course, in a solution of potassium carbonate. So section 1 is related to fracture. I will be very short, even if we have a lot of observation, also a diffused damage in some cases, which evolves in the time, during the time. And lastly, we have real, in some cases, even macro cracks. For example, what you say in the palladium, after 20 hours of our preliminary tests, we had this crack, which was long about 2 millimeters, and the width so the distance between the two crack faces is about 40 microns, 40 microns. This is a micrograph, of course. So I show you only that, but we have different interesting micrographs. Then we have section 2 about chemistry, very interesting, very important in my opinion, just to understand what is going on. I have to say that we used the best specialists in Politecnico di Torino for many years, different years, and they used the EDS technique. It means energy dispersive spectroscopy or X-ray spectroscopy. The first test 1, is we report only the situation at the beginning, before the test, and at the end, after 20 hours. You see the palladium, you see the particular values, which I intend to comment more. Even if we have many elements that were analyzed before and after the test, you see the palladium usually decreases between, in the 4 tests, between 25 and 30%, repeatable, very repeatable. We have the oxygen, which increases between 15 and 20%, and then we have other smaller variations. And I underline the fact that potassium is appearing plus 2% in this case, experimentally. Theoretically, we will see that there is a small deviation. So this is the main hypothesis, that we have fission or splitting. I don't know, as technical we should call it, but there is a primary fission. The palladium, which is 46 as an atomic number, becomes iron and calcium, which are 26 and 20. This is the first, we can say, primary fission. Then a series of secondary fissions, giving us the elements you have seen in the previous table. Please observe also the products. We have neutrons, alpha particle. We see the helium is the ionic particle is an alpha particle, and other products like protons or other elements. So we had just the detail. You can observe the details afterwards, maybe now only the main things about these tables. The last table of this test 1, or first test, is related to the stoichiometric balances, which is very important because they give us, they reproduce exactly the situation we have seen at the beginning with the decrease of palladium and the increase of lighter elements. You see that with the yellow evidence, we have the oxygen transformation. Better to say iron and calcium becomes also oxygen related to this, in relation to these balances. Also, for example, in this case, we have that potassium should be 1.5. So it means that we have, we can say, approximation or deviation of 0.5. So globally, we have 1.7 for of deviation plus 0.5. It means 2.2%, which is on the global is not very bad, I think. Then we had the other 3 tests. They were shorter because we decided that in the second part there were not so important transformations. And I underline or emphasize the extreme values before the test and after 10 hours. But we have also after 2.5 and after 5 hours. So I've not the time to go to the details, but it's very interesting to see that statistically there is an impressive repeatability of the results from the chemical point of view. So we have the assumed fission reactions with neutron and alpha particle emissions. And lastly, we have this table where we have only oxygen as an approximation, or we can, better to say negative term, deviations. In this case, it's 5%. 5%, a little more than before. We were 2.2 in the first, now 5. Then we have test 3, which is absolutely similar to the previous one. I can read not only the numbers, of course, we have these red circles emphasizing the most important. You see that there is not an excess of potassium. And it's very important to observe that potassium is the main element in the solution, potassium, also oxygen, of course. And then we have the same kind of reasoning with this approximation in yellow evidence. Okay, the last is test 4. We have a repeatability, so I don't go to the details, but should be very interesting to make the arithmetic computation, just to be convinced about that. And lastly, I should like to show you this table where you have this approximation or deviation from theory to experiment, with respect to experiments. You see the values that we had for palladium are 2.2, 5, 1.1, and the last is 3.9. Then you see that for the nickel, that I've not commented up to now, we had very small deviations. In some way, they are only a fraction of the previous one, between 1/3 and 1/2. Very small, but I didn't, I have not the time to go to the details for nickel, but also for nickel we have the same kind of analysis. Then we have section 4 of my speech is related to neutron and alpha particle emissions, very important part, because it's also correlated in some way, very strongly correlated in my opinion. Test 1, it was the longest. You see, it was in total, it were of course 1,200 minutes. It means 20 hours, of course. And we had 4 neutron peaks. This is the rate of the neutron emission, the rate. Then we will see the cumulative, which is maybe more clear. But you see that we have a direct comparison between background, which is about 4 CPS, but also there is the power of 10, 2 minus 2, of course. There is the scale, you can see the scale of the neutron emission. And you see that we have on the left a first very clear peak or burst, no? Which is about more than 8 times the background. Then the other 3 are a little smaller, Okay, this is the most important thing I believe to observe. Then we have for the same time period, so 20 hours, we have this cumulative graph for cell off and cell on. It means background and, of course, CPS during the test. And you see that there is a fork of about 60%, which is very considerable result, I think. Then we have test 2 is only 10 hours. It means, as you see in the horizontal axis, we have 600 minutes, and we had smaller peaks, only 2 peaks, even because there is a shorter time, and the first peak is around twice the background. The background in that period was measured very carefully. It was 8, so about 8, so higher than the previous one, and the peak is around 16 of course CPS, etc. Okay, and then we have also in this case a fork between cell off and cell on. It is around 20%. Then we had this test 3, where practically we have no peaks, unfortunately. We have some very small deviations with respect to the background, so we didn't conclude anything. about test 3. And then test 4, we have again 2 peaks, the first of which is a little more than twice with respect to the background. Background is again around 8 in our units CPS. You can read in the top of the slide exactly the value, but in relative terms is more than twice. So is for specialist of measurement of neutrons is not bad. Then we have another fork with 15%. Then alpha particle, I will be a little shorter because we tested alpha particle a little less frequently, but we had this test, for example, is the acquisition time is 1 hour. 1 hour is a sell-off. There is a medium, average, which is about 1/2 with respect with sell-on. You see the difference. And then we have a fork, of course, which is more than 100%, of difference between sell-off and sell-on. Okay, so very, very clear fork. Then I have the last part, which is, I think, maybe the most important. But the global results about heat generation, generally speaking, is not very good from the application point of view, because if we measure the COP over all the 10 or 20 hours, we didn't obtain a value higher than 1. But if you limit your analysis to the yellow rectangle I've shown you, I mean around the peaks, we limited our calculation around the peaks, I repeat. In that case, we obtained values higher than 2. So the computation is very simple. We consider an input energy, which is the energy from the electric network, EIN, we can say, the first term. The second term is energy coming from assumed or hypothetical fuel. And then on the right we have the output energy as vaporization energy and energy transmitted by convection and irradiation. So making calculations very, very easy. COP is the ratio of the output energy over, of course, the input energy. In this case, I repeat, limited to these segments or time periods is around more than 2, you see, 2.43. Then we perform the same calculation of second peak, the third peak, and fourth peak of the first test, and the other peak of the third, second, and the fourth test. I give you the final results in the table, but it's a very simple calculation in this way, it's repeatable, and we have this series of values. You see, always higher than 2, excluding the last where we have 1.63. Oh, 60, yes, 62. So we can say that the phenomenon exists, in our opinion, is absolutely evident and repeatable, even if from the technological point of view, maybe there are some problems, of course. Thank you very much for your attention.
Thank you, Alberto. So now if you have any question, it's time to tell your question. I'm hiding, that's all. Okay, there are questions here. Bob. No, he has a question.
Yes.
But there's no mic. Okay.
Have you considered the pure fission reactions and exchange reactions for the accounting for the nickel and iron? And then secondly, did you do residual gas analysis and see if it was argon?
Excuse me, could you repeat the first question?
Did you consider pure fission reactions?
Pure fission, yes.
And exchange?
Yes, fission reaction with excess neutrons in any case.
Okay.
In the second question, excuse me.
So there's a fission reaction from palladium that produces argon and nickel, which that produces isotopes of both 38 and 40 argon and nickel 64 and 62, respectively.
Yes, yes.
Did you look with a residual gas analyzer to see if you saw
No,
argon?
I can answer that. Unfortunately, we didn't have any particular control about volatile elements like
Noble gases or something?
Yes,
Yeah, okay.
no, argon also.
And also, if you include weak interactions, you get direct production of fission with weak interactions of potassium and nickel as the fission products, which you both observed. Without none of those reactions involve neutrons.
Of course, we had made a very analytic study that was presented yesterday by Domenico Scaramozzino. Is according to the Cook's model, which in our opinion is the best model on the market that could in some way reproduce this kind of fissions. And in any case, I don't like to speak about fission. In some way, it is a balance also in that case, is a balance, a nuclear balance. So maybe that are not the classical fissions of uranium. And so I use the word fission, but really are the hypotheses about this kind of, of reaction. What I want to say that I cannot exclude many more different reactions, no, of course. But in this case, this hypothesis, precise hypothesis, which could be criticized maybe, but it can reproduce nearly exactly what we have chemically.
Okay, there's one other reaction you could consider, which is exchange reactions between oxygen and palladium, going to directly iron and nickel, and there's about 15 possibilities.
Palladium is our hypothesis, because this reaction should have been in a very short time after the beginning. Is palladium splits, in our opinion, in our hypothesis, into calcium and iron. Then calcium and iron develop oxygen mainly, and other elements or fragments like neutrons, alpha particles, etc. So our feeling is that when we say that there is I want to say helium, no? For example, I remember that I spoke with Arata, that I remember many years ago, it was 2010, he told me that he was not so happy about the results because helium is always too low percentage of helium. So in our hypothesis, they are alpha particles coming from this disgregation, disintegration, we can say, of the nucleus.
Okay. Okay. Any other question? Yeah.
In your COP calculation, you introduce a hypothetical energy, right? Would you tell me about...
I introduced?
You introduced a hypothetical energy, something like that.
Hypothetical?
Yeah. What is...
Yes, the full, yes. But it really is not well known. So I want to say that it's not a result from our experiments. It's exactly what, so you have the output energy minus the input from the network, you have this energy. So it's a hypothesis that there is a fuel. Of course, our fuel...
okay.
Okay, I don't know if the fuel is hydrogen, as we think usually with cold fusion, or palladium itself.
Okay, thank you.
Please.
Any other question?
Or nickel also.
I have two questions. What's the temperature of your cell? The temperature?
Temperature, yes.
What is the temperature?
The temperature...
Can you talk to the mic, because they will not listen.
The cell was about 55.
55 degrees. And second, how do you measure the alpha particles? You have to put a detector inside the cell?
Yes.
Inside the calorimeter?
No.
The alpha particles cannot go through. They are blocked by the liquid, isn't it?
Yes, it was not inside, it was outside. And then we had the residual part.
Okay. All right. Thank you very much, Alberto. Our next speaker is, I don't know who. Who is the next speaker? I don't know program. Is this program correct? Professor Iwamura is going to talk now. I'm very happy that he came here. I'm always very impressed by his work.
Thank you.
So it's an honor for me to introduce him.
Good morning. My name is Yasuhiro Iwamura. I will talk about anomalous heat triggered by input power perturbations observed in nickel-based nanostructured thin films and filled with hydrogen. Okay, here's the background. I have been working a very long time in this field, and when I was a researcher of Mitsubishi Heavy Industry, I engaged in the experiment of transmutation. In the transmutation experiment, we use palladium and calcium oxide multilayer thin film with deuterium gas. We put this kind of multilayer and we put the cesium and we make a permeation flow through the palladium multilayer. And we observe the cesium to praseodymium transmutation reactions. And after that, I moved to Tohoku University, and I had a chance to participate in the NEDO project, Japanese NEDO project. In the NEDO project, we use nanoparticles, mainly copper and nickel and palladium nanoparticles. And we observed anomalous energy using this particle and hydrogen or deuterium gas. So combined, based on these two research activities, we invented the present method, excess energy with nanosized multilayer metal composite and hydrogen gas. We are now collaborating with venture company Green Planet, and now they are trying to commercialize this technology. Anyway, key factors in the present method is hydrogen diffusion and nano thin film and vacuum conditions. Okay. So, and recently we call this LNR or cold fusion phenomena quantum hydrogen energy, QHE. It is defined anomalous heat generated by quantum phenomena during hydrogen diffusion process in nano-sized nickel-based composite metal. Because this QHE is for the public acceptance, because many people do not like a term of nuclear. So we invented, we started to call QHE. Okay, anyway, I would like to explain our method. We use two nano-sized multilayer metal composite, like this one. Before experiment, this is a nickel bulk and copper, nickel, like this. Usually, standard one is copper is 2 nanometer, and nickel is 14 nanometers, usually. It's a standard sample in our experiment. And we prepared two samples, and they are heated by the ceramic heater. Okay, and temperature measurement or heat estimation is by the usually TC, thermocouple embedded in the ceramic heater. And also we check the surface temperature by infrared, surface A and surface B. And at the beginning of the experiment, we introduced the samples into the chamber and baking the samples to remove the mainly water or carbon or something like impurities. And after that, hydrogen gas is filled in the chamber and hydrogen absorption. And after that, we evacuate the chamber by turbomolecular pump and simultaneously heat up the sample up to 500 degrees centigrade. By doing this, hydrogen atoms absorbed and the nickel bulk released, diffused through the merge layer, okay? And then we observe the excess power, anomalous excess heat. Okay, so this is photos of copper nickel merge layer film and experimental setup. This is the chamber, and in the center we have this sample, and also we have radiation thermometer A and B. Okay, now this is the model of excess heat evaluation. During excess heat experiment, it is under vacuum conditions, so we consider only heat conduction and thermal radiation only, no convection by helium H2 gas. So this is a heat conduction term, and this one is a thermal radiation from the surface A and the surface B, and the radiation from the holder, sample holder is here, is equal power input plus excess heat, okay? And using this equation, for multi-layer thin film, P in plus excess heat, and for nickel bulk, we assume that no excess heat. Actually, only nickel bulk have some excess heat, but in our case, we estimate the multi-layer thin film effect only, okay? So we use a blank run. This kind of calibration curve we get. For the blank run here, it's for nickel bulk only. This one is multi-layer nickel bulk and multi-layer curve here. So for example, if we input 20 watt, we get 800 degrees centigrade, for example. And in the case of a multi-layer thin film, we get 860 degrees centigrade. So we can observe the delta T, the temperature difference between multi-layer and blank. So based on the model, excess heat can be expressed as a function of delta T. So we can estimate by the delta T excess heat. Okay. Oh, oops. This is a typical one, and I already show sometimes. But in this graph, blue point means pressure in the chamber. It's a pressure of hydrogen. At the beginning of experiment, we gave about 230 Pascal, not so much. And samples absorbed hydrogen like this. And usually we start evening or next morning, we evacuate the hydrogen gas and simultaneously heat up. In this case, 19 watt is applied to the ceramic heater. And we got this red point is excess power, and we have about 5 watt excess heat. So in this case, we input 19 watt and we got 24 watt, okay? And using this method, we repeat this kind of experiment and to check the reproducibility. In this case, if we input 90 watt, we got this almost similar excess heat. And if we decrease the input power, we also more smaller excess power. And based on this data, we can calculate the total absorbed number of hydrogen gas. Hydrogen atoms is here. And if we integrate this excess power by time, we got total excess energy, 1.1 megajoule. So we can estimate the excess energy per hydrogen gas. It is 16 kilo EV per hydrogen. It's usually chemical reactions, electron volt order, and the nuclear reaction is mega electron volt order. In our case, we got the 16 kilo EV. This value cannot be explained by known chemical reactions. And not all the hydrogen could not react. So maybe this reaction caused by nuclear reactions. Okay, so I would like to mention about the heat burst phenomenon. And sometimes we observe the spontaneous heat burst like this. This is data for example data, and this is the excess power and the time. At the 950 degrees centigrade, we have many heat bursts here, and also here we have a heat burst. And this heat burst, we magnified view of time that the heat burst occurred. We can check the closely like this. Red line means TC, some couple in the center of the ceramic heater, and green correspond to surface B, and blue correspond to surface A. In this case, at this point, spontaneous heat burst occurred on the surface B, and temperature increased at about 20 degrees centigrade and propagate to the center of the some couple. Okay. And this is an example of spontaneous heat burst occurred on the both sides of copper nickel 7 standard sample multi-layer composite. In this case, this is the time, and this axis means the sum couple temperature is the surface temperature. And at this point, surface A, on the surface A, spontaneous heat burst occurred, and surface temperature increased up. And after that, at this point, at this time, surface B, spontaneous heat burst occurred. And they propagate to the center of the sum couple. And we got this kind of sum couple temperature time variation. Of course, during this phenomena, we did not give no extra energy. It is room temperature and a real power input. So it's just a spontaneous heat burst. Okay, so we observed this kind of a spontaneous heat burst. So we would like to control this heat burst phenomena. So If we investigate this heat burst phenomena, spontaneous heat burst phenomena in detail, we found that at the spontaneous heat burst, it was induced by maybe input power fluctuated slightly. So we intentionally give the fluctuation, perturbation of power input. So this is the power input fluctuation. And if we give the power input perturbation, temperature distribution in the sample, and the disturbance of hydrogen diffusion would occur. And we finally get the successfully induced heat burst intentionally. Okay, this is a typical result of a intentionally heat burst. In this case, we use a copper nickel standard 1, and input power is here. At the beginning of the experiment, we applied 25.8 watt and slightly decrease and back to the original value. Okay, and after that, at this point, heat burst occurred on the surface B, and after that, at this point, heat burst occurred on the surface A, and they propagate to the center some couple here, like this. So surface temperature A and B and TC all increased significantly, like this, about 20 or 30 degrees centigrade input power up. Even though input power was once reduced, we did not give any extra energy in this case. And increases in surface A and B were larger and steeper than that of TC. Heat burst energy at the surface A and B propagate to some couple. Okay. And the other one, nickel bulk case, we cannot any heat burst if we give the same perturbation like this. In this case, we gave the perturbation, but no effect. Nothing happened in this case. It's a normal one. Okay. And we estimate energy generated by a single intentionally induced heat burst. And it cannot be explained by any known chemical reactions. Okay. In this case, this is the intentional heat burst region. So in this case, it corresponds to here, and we extend the time span, and we have this is the sum couple temperature. The sum couple temperature significantly increase and gradually decrease. And this point corresponds to 6 watt, and this one is correspond to 5.6 watt. So at least energy released by a single intentionally induced heat larger than this region. So 4.8 kilojoule is obtained. But during the excess heat experiment, they are under the vacuum conditions, and so we have, we have some residual gas in the chamber, and but number of residual gas is very low. So hydrogen and sample oxidated, if we postulate by the O2 residual, this part. So they are about the 10 to minus fourth to 10 to fifth force. So it is not so large. So it cannot be explained by any chemical, even though for the single perturbation reactions. And I would like to show about variation. Usually, this kind once reduced and back, and we observe the intentional heat burst. But in this case, ratio of the copper and nickel is different. And in this case, a little bit different. At the surface B, at this point, heat bursts occurred, and also at this point, heat occurred. 2 heat bursts occurred. And on the surface A, at this point, heat bursts occurred. So at present, variation in the way heat bursts occur due to the parameters of input perturbation, sample surface conditions, and hydrogen absorption conditions, and other factors. So anyway, we are now trying to clarify what is happening. So these data will be useful to make clear this phenomenon. And next point is the results of SEM analysis. It's a SEM analysis for heat-producing sample. We found some common features, common characteristics of the samples in which excess heat was observed. We observed this kind of spotted region within the grains. This is a comp image by backscattered electrons. We can see the spotted region. Maybe this corresponds to this means elements lighter than nickel. Mainly we have a nickel. So after that, it is the presence of oxygen element. Okay, I will show you detail. This is a semi-EDX analysis for spontaneous heat bursts. I introduced these 2 spontaneous heat bursts occurred. In this case, we can also observe the dotted point like this. And at the dotted point, we can see that the very large oxygen concentration here. But normal point, as we cannot see any oxygen like this. Areas such as black spots has very high concentration, while the other have no oxygen concentration, okay? And this is analysis for intentional heat burst sample, this one. We also black point here, and at this point, it's 32.88%, a very high concentration here, but the normal point, no oxygen here. And for the sample, we measure the top SIMS, time of flight SIMS analysis, and we get the depth profile for this region. And we can see that this is the depth and total counts by total counts. We can see this is a region for this is the bulk region and the multi-layer region here, okay? And we can see that the very high concentration of elements here, and nickel oxide, and other elements here. So O minus is the most abundant present, more than 40%, according to this Tufts SIMS analysis. And so we would like to say that SEM EDX analysis and the Tufts SIMS analysis give us consistent result on oxygen concentrations. And so we can say that the regions of high oxygen concentration were also observed in the samples with intentionally induced heat bursts and also spontaneously heat burst sample. And after that, we tried to force oxidation. This sample was taken out and oxidized at 500 degrees for 2 hours in the air. So this sample expected to have a very high oxygen content concentration. But after the experiment, maximum value at the forced oxidation sample is 4.56, lower than that heat-producing sample. So normal area, even in the heat-producing sample, non-detection of oxygen concentration. And but and highest oxidation concentration in the forced oxidation sample, less than 5%. Even though forced oxidized, but 5%, less than 5%. But very high oxygen concentration at black region in the heat-producing samples, larger than 10%. I would like to say it is anomalous results. So we will consider about the oxygen concentration anomaly more and more. So it is just an assumption, but I would like to discussion about the data. The perturbation of input power causes a fluctuation in the hydrogen density, which might trigger the heat burst phenomena. We are currently attempting to explain the phenomena by trapping hydrogen. Maybe many hydrogen trapped by the vacancy or dislocation and voids and something like that. So we are now trying to explain about the heat burst phenomena. The hydrogen absorbed in the bulk and in the mixed layer, and the hydrogen inside diffuse evacuation through this. And many hydrogen atoms can be trapped in the trapping site, such as vacancy and other point, we assume. Now, that is just an assumption, but we are trying to clarify this phenomenon. And I would like to, one more point, research implication of observing heat burst. Excess heat generation is usually using a calibration curve between the nickel bulk and the multi-layer thin film sample. Someone questions or doubts whether the heat dissipation conditions are different between the time of calibration and the time of heat generation experiment. But since the heat burst phenomena were observed under the same heat dissipation conditions, it cannot be explained by the difference in the dissipation condition between the calibration and heat generation experiments. So observing heat burst phenomena enhances the reliability of excess heat experiments. Okay, I would like to conclude my presentation. Innovative method to induce enormously large heat generation phenomena that cannot be explained by any known chemical process has been developed. Nickel-based and nano-sized multi-layer thin film was preloaded with hydrogen gas and heated rapidly and diffused hydrogen and induced heat generation reactions. Not only steady-state anomalous heat generation, but also spontaneous heat burst phenomena sometimes observed. Based on the observation of some spontaneous heat bursts, intentional heat bursts have also become possible. Even a single heat burst phenomena cannot be explained by any known chemical reactions. Observation of heat bursts has improved the reliability of excess heat experiments. Samples that generated excess heat or a heat burst often show some regions of very high oxygen concentration, higher than in the first oxidized sample, after the experiment, according to the same EDX and the TOF-SIMS analysis. Okay, thank you very much. This is acknowledgement. Thank you very much for attention.
Thank you very much. It's a very excellent work. This is open to questions now.
ありがとうございます。
Okay.
Iwamura-san, I have a question about the proportionality of excess produced. You observe that you have a proportionality of excess produced as a function of the stimulating heat that you inject into your sample, right? When you heat your sample at a certain level, you have more or less heat generated.
Yes.
Do you see a proportionality into the heat produced when you have different levels of vacuum?
Oh, different, depends on the vacuum level and excess heat.
Do you see proportionality in such?
We usually perform under about turbomolecular pump level. And if we decrease the, if we omit the turbomolecular pump and usual pump, excess heat decrease. But we did not systematic data about the hydrogen, the vacuum conditions. So maybe high vacuum condition is better, I think. So impurity on the surface is very crucial. Okay.
Any other question?
Thank you very much for this very nice presentation. And do you believe that it is possible to increase the heat excess, for example, building up a wider surface sample or a more structured multi-layer composition?
Yes, I think so. So we are now trying to trying to get more power by doing increase the surface area, but it will be not so easy. But anyway, basically it is possible, I think. Okay.
Okay. In one of SEM analysis, you show the presence of manganese.
Yeah.
Can you comment about?
Yeah. It's a very good.
Because manganese has a strong effect about oxygen concentration and so on.
You're talking here, manganese.
Yeah.
Yeah. I sometimes a very large amount of manganese, and maybe it is not concrete results, but sometimes anomalous manganese we detected. But at this point, we cannot say concrete results, concrete conclusion. But sometimes clear anomalous manganese we detected. I suspected some transmutation reactions occur in this multi-layer thin film.
The last question? I'm sorry.
Okay, thank you very much for your very interesting presentation. I have one question and one remark, please. Concerning the heat burst, I guess you made many different tests of heat burst. You have the statistics, how many heat bursts responded to this heat change?
Statistics about the heat burst, intentionally heat burst statistics. Okay. If we use this kind of, we call standard one, copper 2 nano and nickel 14. And in this case, if we use almost every time we observe, mainly 90% or so, we got. But if we use another type sample, it depends on the very different.
Thank you very much. And the last point, I know that you name this energy quantum hydrogen energy because you explain that cold fusion or nuclear energy will not be acceptable for commercial purposes.
Sorry.
You use QHE.
QHE, yeah.
Yes, instead of cold fusion.
Yeah.
Is it important in your view to use a different word, not LNR, not cold fusion, not...
It's just public to public acceptance. In the point of view public acceptance, we use QHE because everybody do not like a nuclear term, so we omit. And instead of nuclear, we use a quantum. That's it.
I fully agree with you. Thank you.
Thank you. Okay, go ahead. Yeah. And we have one last question from Conrad. He's my boss, so he has to ask.
No, the question is related to energy balance you have presented here. So this function between the heat excess and the difference of the temperature you presented. So you can explain this function using your energy balance, your function you have presented, or
energy balance for?
Yeah, this just first slides you have presented. Energy balance, heat transfer, and there was a function between heat excess and the difference of the temperature between, reference sample.
You're talking about the consistency of
yeah, exactly. About
TC and surface temperature?
No, this is just the first. Or maybe we can discuss this later.
Okay.
Yeah, I think we can.
Only one question. You have maybe started also some experiments with deuterium to compare hydrogen and deuterium.
Yeah. I have much interest in the experiment of deuterium, but we did not perform this kind of experiment in our experimental, because if we input deuterium gas, maybe after that the inference will be prolonged. So I did not. But Professor Kasagi sometimes do using other experimental device.
I think. Thank you very much. We have to stop.
Can I ask two quick questions?
I know you talk too long all the time.
Very quick.
It's not possible for you.
It's shorter than this interchange.
Okay, say it quickly then.
Do you, thank you, Irma, do you see correlated radio emissions when you see the heat bursts?
Radiation emission?
Radio frequency emissions.
Radio frequency, no, we did not.
Could you look at that with AM radio? And then the second one is, have you considered using silver instead of copper?
Silver?
Yes. It's diamagnetic, and copper doesn't absorb or adsorb hydrogen, right. So it does concentrate it. It's diamagnetic and conductive, so.
Okay.
And it's got spin.
Good. Thank you very much, Dr. Iwamura. Now, where is the next speaker? And let me see. I have. The program is the same after. So that's good. Where is Dr. Dubai? Dubai? No, not Dubai. Dubai. Dubai is another place.
Maybe you want to see also here. Sorry.
Good morning, all of you. Okay. Good morning, all of you. In this talk, I'm going to present the experimental studies of the internal pair creations in the DD reaction for the cold fusion experiment. And this is our team from Elbrus Lab, University of Iceni. So outline of my talk is following. First, I'm going to start with an overview. Of observation of the fusion product produced by the DD reactions in cold fusion experiment. And for the completion of this observation, I have taken the example of the helium-4 production and its correlation with the cold fusion experimental setups. And later, I tried to understand this helium-4 production at the theoretical fronts, and we tried to measure the decay of the internal pair creation originated from the helium-4. And we'll discuss our result and how we can go further. So, okay. So if you look at the DD reactions at very low energy, there is the two most dominant prominent channel and equal probable, helium-3n and triton proton. But there is another weaker channel of the 7 order of magnitude, helium-4 and gamma. And if you go to the look the branching ratio at the setup of the DD fusion in metallic and gaseous environment, at room temperature, the helium-4 production become the most dominant channel, especially without gamma. Helium-4 production without gamma become the most dominant channel compared to the other two. So if you want to measure the branching ratio, first we need to measure the fusion product. And how we can measure the fusion product? We can measure the fusion product either with the charge particle detection systems or with the low energy accelerator facility. So with the charge particle, if originated from the gas discharge setup or the electrolysis setup or diffusion, people usually prefer to put the CR39 detectors, and CR39 is a polymer, and when charge particle passes through this polymer, it creates the damage, and with the calibration of, with the help of radioactive source calibration and you can say light ion beams, interpolate the nature of the particles. And for the neutral particles, usually prefer to put the organic or inorganic scintillator detectors depending on what kind of physics you are looking for, or simply you can put the neutron counters like BF3. And for gammas and X-rays, you can take the sodium iodide and germanium detectors. So I have taken this slides from the recently concluded very nice presentation given by Eric Jem from University of Illinois, and where he has measured the helium-4 using the CR39 his DC glow discharge palladium with the palladium electrode setups, and he observed the helium-4 with the energy of around 100 keV, no helium-3, no triton channels, and this helium-4 is the without gamma, and this is the same of CR39, and this count he has estimated with respect to the minor axis and energy loss along with the track. So for the filtering, for further filtering, the source of these counts, he performed the machine learning approach to look from where the origin of this particle. So he found that these particles, helium-4, is originated from the palladium surface. So for the neutron observation, if you, I have started at the beginning. So this was the first and foremost positive result in cold fusion with the cold fusion setup, where Jones measured the neutron counts for these electrolysis setups with the help of the liquid scintillator detectors. But if you look his neutron measurement, it's lying around the backgrounds, lying around. Even he has added few counts, and the poor it had poor statics, and just after 6 months, there was very nice experiment done by the Benel group, led by the Guy, and where he measured the. When I say nice setups, he had at that time they had put the 4 liquid scintillator neutron detectors side by side. At the top, 2 plastic Beto scintillator detectors, and as well as at the side they put the gamma detector, sodium iodide, 2 sodium iodide detectors. And what they observed, there is no gamma, no neutron, and even this neutron, what claimed by Jones, it's coming from the background. But if you look this work, interesting thing what they didn't mention about the heat excess as well. So it means they didn't observe the heat excess as well. So here, though they declined the Jones work, but where Jones said that heat excess is there and neutron observed. So I'll come to the recent measurement performed by the Thomas Senkel at the Berkeley lab. This is his gas discharge setup, and this is the EJ312 scintillator detectors, and they put the sodium iodide detector, and with the different applied cathode bed voltage, they found that this neutron count detection rate increases if increasing the applied cathode voltage. So main point, if you look here, again the software front and data acquisition set up, they approach it different way with the help of the kind digitizer PSD, and this Q int is the total charge integration. If you look, there is dotted blue lines, and this is the solid black lines. So solid black lines correspond to the bare nuclei without considering the screening effect, and this is dotted line the screening potentials with the 1250 electron volt. So if you look the cathode voltage around 2.5, this almost this neutron yield is well fitted for this screening potential, and the order of magnitude is like 4 order of magnitude difference with and without screening effect. So if I would like to summarize the observation, like still we have some challenges with the correlation and correlation of the heat excess or cold fusion product, and reproducibility, and limitation is the material properties changes as per the pressure, temperature. And so as I said, I have taken one example, helium-4 productions and heat excess. So if you look at the helium-4, so if you look at the helium-4, this set of electricity setups performed by the Bush et al., and where he has very nice mass spectrometer, and he measured that always helium-4 productions, not helium, no other channels, helium-3, and the current was around 660, and yeah. And another helium-4 measurement performed by the Michael, and where he measured the helium-4 productions with and heat excess, and he observed the direct correlations, and the slope of this correlation is the Q value of helium-4. And again, I would like to mention this very nice measurement performed by Eric. So he observed this CR39 with his gas DC glow discharge setup. So if you look finally, yes, helium-4 production correlated with the cold fusion experiment, but foremost important things we need to the theoretical model for better understanding of the helium-4 production. So however, so far we are missing the well-accepted theoretical model. So there is recent theoretical work performed by Professor Konachevsky, and where he is saying that helium-4 can form the DD threshold resonances due to the weak coupling between the 1+3 and 2+2 cluster. So after helium-4 formation at DD threshold resonances, next question, which path will be allowed to be decay? And if you look the decay path, either it can decay via the 0+0, or internal pair creation or internal conversion. And 0+0 will be not allowed because of the electromagnetic selection rule. and only there is two possibilities. Either it can decay via the internal pair creation or internal electron conversion. So if you solve the probability transition matrix and you find that decay probability for the internal pair creation is almost 10 order of magnitude higher than the internal electron conversion. So okay, it's internal, this helium-4 will decay via the internal pair creation. So how the spectra is going to be look like? So again, if you look the probability of the probability distribution of the pair productions and with respect to the energy. So a spectra is going to be the, for 24 MeV is going to be look like in this region. So how we measure the internal electron, internal pair? For that we need very good ultra high vacuum setups, and this is the setups we have at our lab, and this setup is with having ECR ion source and very low emittance and high current and stable current. So this is the target chamber, and this is the target detector holder with aluminum foil, and this is our electronic setups. And we acquired the data using the TUCAN-based MCA. So this was our experimental setups, where we have bombarded deuterium beam energy with the 6 to 16 kb, and the target was the 0.5 mm thick, and first we have taken the little bit thicker detector with the thickness of 1 mm, and the surface area was like 100 mm square, and the target temperature was around 20 to 50 degrees centigrade. Again, it is depending on the how much current intensity during. So yeah, so we put the aluminum foil for two reasons. First is to protect the deuterium to protect from the deuterium scattered deuterium beams, and second is we try to filter the clean event with respect to the other charged particle like helium-3 and triton. So here, if you look the charge spectra, this is the proton line and triton line you obtain. And interesting things, if you look in this between this region, there is some counts. And what is that count? And first we try to look with respect to the backgrounds. And we found that this region is not, this counts not originated from the background. So we confirm that this is the genuine reaction count. However, for the further confirmation, we performed a series of experiments with different metallic target and different detectors with the foil thickness. And the foil thickness is like this. First we started with the, again, 1 micrometer, and then 3.7 and 11 and the corresponding, we have taken the thicker and more thicker detectors, and the energy range was almost same. So what you observed, for the thinner detectors, we can see thinner detector with the thinner foil, you can see all the 3 charged particle spectra. And if you compare with the backgrounds, almost in this region, almost the background is there. So, but if you look the more thicker detectors and the little bit thicker foils, in this region, with respect to background, there is some genuine count. And here, broadness, because of the this detector resolution was not so good at that time. So, 1 mm and 2 mm, you can see in this region there is some nuclear reactions count. So how we confirm and how identify the net? how identify the nature of the these counts. So first of all, we need to do the proper calibration with the, and we perform the calibration with the different beta source like thallium and cobalt, and this was the for the different thickness of foil and different thickness of foil and different thickness of detectors. So, and here you can clearly see that the difference. And for example, here this is the Q value of the 204 thallium, and there is the two Q value, 345 kV and 763 kV. So far, and this is the this is done for the 1 mm thick detectors and around 5 micrometer thick aluminum foil. So, yeah. And you perform the corresponding the GANT4 simulation. So finally, we said found that around 1 MeV electron can be stopped by this 1 mm thick detectors. So, so finally, we confirm that in this region, this is the region where electron could be, and 0.6 to 1 MeV, and this is roughly 42% of the total count. So, further you perform the electron-proton branching ratio, and if you look this branching ratio at lower energy, around 4 to, if you go to the lower energy side, this branching ratio started to increase, and it inferred that the helium-4 production in direct wave helium-4 production started to dominate, and this solid lines correspond to the proton width of the 40 MeV, and dotted line is the different with the dotted line is with interference and without interference. So it can be it could be easily explained with the, and more detail you can find in the Conrad talk about the theoretical calculations, but it could be easily explained with the screening effect and the interference of non-destructive interference of the non-destructive interference of the this proton with respect to proton width. So I would like to summarize as a first of all, we need to start with the correlation of dominant reaction channel and heat excess successfully will be proven. And for example, I have taken here helium-4 productions, and we try to understand the theoretical modeling for the consistency and correlations, how it could be correlated with the heat excess and cold fusion setups. And next what? If you look this helium-4 decay, and from decay this internal pair creation can really solve the long-standing cold fusion consistency problem or not. For that, we need to do the further instrumentational development and validate for all kind of setups, not only with the accelerators, but for the diffusions, plasma, and electrolysis setups, and try to repeat the process until the consistency and correlation well established. Otherwise, again, we need to go for this feedback loop. And when I say the instrumentational development and validation, I'm talking about the annihilation radiation and the Bremsstrahlung measurement for this 24 MeV Bremsstrahlung originated from these pair productions. outside the cold fusion experimental setups. So how we can do? For example, we have just started to measure the Bremsstrahlung with the help of the big sodium iodide detectors at our lab, and this is the chamber side. And we observed some gamma, but we are not sure about whether it's coming from the Bremsstrahlung. So we are going to perform some kind of coincidence and another better delta E telescope setups, and then we'll try to look the how this Bremsstrahlung is coming from. So thank you for your kind attention.
So we have time for a few questions. There's a question here.
Thank you for this presentation. In the beginning, you said that this helium-4 production with the gamma decays, as you know, is a strongly suppressed way of production at kV energy. So the statement that this way of helium-4 production is dominant at ambient energy has no evidence at all. It's something that has been proved as just an hypothesis. And then I have another comment. You in the electron measurements, you just measure one electron, not a couple electron-positron. So how can you distinguish between internal conversion and electron pair production?
Actually, if you look, so if you look at our simulation also, so if you look the simulations, not only experimental measurement, you perform the simulations, and from that simulation point of view, you are saying that it's coming from the electrons. So, simulation. Yeah, J&4 simulation. So, so if you look in this region, this red lines for the 1 mm thick silicon detectors and 5 micrometer, around 5 micrometer thick aluminum foil, and there is the red line, and and there is another black solid line. So this black solid lines, I consider only the electronics part. So, yeah.
Yeah, but I do not see this. It's too small, this plot. I cannot see anything.
I think we should keep that for the coffee break that will come in after Professor Jeski's talk. Okay. Thank you very much. Okay. I think we have to continue, otherwise there will be no coffee break. Our next speaker is Professor Jeski. You can come on stage.
Ja, dus als je Okay, thank you. Okay, so you can hear me or not? Yeah, I would like to have more space. Okay, so the objective of my talk is to present you how we can conclude about room temperature reactions, studying DD reactions at higher energies using accelerator systems. You can hear, it's much better than I come more closer. Okay. So once again, we measure usually dp dn reactions, which dominates at higher energies, at kV energies in accelerator experiments. And as said Rakesh before, gamma channel is suppressed by a 10 to minus 7 factor. So it is really very rare channel. So usually we see neutron and protons at the same level. Branching ratio is about 1. So coming to the beginning of my talk, I would like to show you that some problems in DD cold fusion we could resolve, we could find a solution based on these results. And I would like to present you how we can do it. So the main point was penetration through the Coulomb barrier, and the solution will be electron screening. And another point is that the branching ratio at very low energies, at thermal energies, seems to be completely different, that helium channel dominates, and there are many experimental indications for that. And then the third point is the pure reproducibility, but because of even small impurities, changes in the lattice, defects in the lattice can change completely the screening effect and then the final reaction rates at thermal energies. Okay, so how we can do it? First one, and this will be talked about it by Natalia Targosz-Lęczka in the next talk. So very briefly here, we have a Coulomb barrier we should tunnel, and then you have here Coulomb interaction, Coulomb potential, and here a screening function. We can describe it by a screening energy with the screening length that reduce this reduction of the height of the Coulomb barrier, and then the penetration factor that describes this tunneling effect can be described very easily. If you have the screening energy, we put additional factor to the energy, and then we can describe this tunneling effect in the presence of the electrons, surrounding electrons in some materials, mostly metallic materials. Okay, so you see here there is a exponential function, and therefore we will expect that because of the screening, we will see increase of the reaction rates going towards lower energies. And this is really the case, or this maybe before, this standard experimental setup that has already, there is a lot of history. We started to measure these reactions already more than 20 years ago. And already through that time, we used different Ford detectors. We measured the angular distribution of the reaction. Here you see the example of the spectrum, charged particle spectrum using silicon detectors. You have protons, tritons, and helium-3 particles. And even at the lowest energies, we measure that the angular distribution is not isotropic. Okay, and there's the result that there's already, as I said, a long story behind. And you see here's an enhancement factor. So we compare reaction rates to the theoretical one without any electrons, because DD reactions are known very, very well. The cross sections are known, studied many times in the 50 last years. And therefore we can calculate this enhancement factor as a ratio between experimental cross-section we measure to the theoretical one that is determined for bare nuclei without any electrons. And what you see that different targets, so the deuterons are implanted in the metallic targets, and then we can see that the cross-section in these different environments increases differently. And one parameter that is needed to describe it is the screening energy. And the screening energy is different for different materials. It is much higher than for gas target experiment measured before. It was 25 electron volts, and in the case of tantalum, you see here 300 electron volts. There are many other experiments made in the last 20 years, and this discussion will be made by Natalia. So I wanted to show you, however, the same slide Rakesh presented before. Maybe once again here, you see that the enhancement factor is maximum about 2. We could measure the lowest energies. And the question is, can we extrapolate these curves down to room temperature, to the thermal energies, milli-electron volts, and hope that this exponential increase will be much larger? The answer you can find here in this diagram, this measurement of neutrons in discharge experiment. You have the voltages of this setup was up to 13 kilovolt, and it is really very, very nice work. It is of course difficult to say what was the energy of this of DD reaction here that took place, but if you calculate theoretically very, carefully, and you can take different energy loss models for that, you can produce a kind of this diagram, and you see that enhancement factor, so experimental one to the theoretical, this black solid line is about 10 to 4. So it is 10,000 stronger compared to the theoretical prediction. So this illustration for that even at low energies, you have this very strong increase. So you can, so from the experimental point of view, we can extrapolate down our experimental data. Okay, so comparison between experiment and theory of we measured at different metallic targets, and there is the theory we have developed already 20 years ago. For different materials, we have used so-called self-consistent dielectric function theory that is usually in plasma physics, and there is contribution from free bound electrons and cohesion screening in the metal. And you see the experimental results measured 20 years ago are much higher than the theoretical prediction. So the theoretical prediction is of the level of 100 electron volt, and we measured 300 electron volts. But if you change the parameter here, we have studied not the atomic number, but the average distance between electrons in electron gas. So you see that this characteristic structure that we observed can be reproduced by theoretical calculations. And Thomas Fermi approximation without contribution of the bound electrons give no structure anymore. So we can reproduce the material dependence you have measured very nice. But there's still a missing factor of 2 or 3. And the last measurements show that we can reduce this factor to 1, and our new experimental results are just in agreement with the theory. So the point how we can reduce this screening energy, it is something what we have found last years, that this increase is a result of the crystal defects that can be produced by deuterons in metallic targets. And then we can introduce effective electron mass, and the screening energy is dependent as a proportional to the square root of the effective mass. So if you have more crystal defects and different kinds of vacancies, dislocations, and so on, some impurities that can play a role here, we can reduce this experimental observation in ultra-high vacuum to this theoretical level. So I want to show you the results we have obtained at ultra-high vacuum for very clean targets that was cleaned before by argon spattering, so we had no impurities for a short time, let's say several hours. And then this enhancement factor, once again, looks, experimental one, looks something like this. And however, the screening curve, the blue one, cannot describe it very, very well. So you see systematically our experimental data are below this blue curve for energies above 10 kV and above, systematically above this curve for lower energies. So the screening alone is not okay to describe, or it's not enough to describe this situation. And then is what is necessary to put here, to include here a so-called threshold resonance that is placed somewhere at zero energy, and we see only a high energy tail of this resonance increasing this reaction rate. So if you put this resonance additionally and assume interference effect of this resonance with other broad resonances in helium-4, we can describe this curve very, very nice. So the result of this experiment, that's new screening energy is very close to the theoretical one we have predicted 20 years ago. And the partial resonance width of this resonance is 40 millielectronvolts for the proton channel. So it is very small value. Usually in nuclear physics, the resonance width is about 1 MeV. So this very narrow resonance that should be placed very close to the reaction threshold. And for comparison, you see here as a gas target. And in this case, gas target measurement, and this case we have once again the same situation, the blue curve describing only screening. No, here is different here. So only screening is the red one, red curve. And the blue one is screening plus resonance. And once again, we can describe the cross-section very well. And the screening energy is here, in this case, 20 electronvolts, what we expect theoretically. And the partial resonance width for protons is 10 millielectronvolts. Okay, so this total cross-section we have observed, but we could see this resonance also in the branching ratio, neutron-proton branching ratio. For some materials, strontium, this branching measure we have observed some time ago is decreasing, so neutron channel is suppressed a little bit. If you have this resonance, we can describe it very well. For tantalum and let's say zirconium, we observe a standard branching ratio equal to 1. So in this case, even in the situation of the angular distribution, we can describe all the observables assuming that we have this threshold resonance, very thin, very narrow threshold resonance, and we have different partial widths for neutrons and protons, and therefore we can use this threshold resonance as a, as a method to increase helium-4 channels to enhance this channel additionally. So what is the situation in helium-4 from the nuclear physics point of view? So we know very well the sequence of the levels of helium-4 excited levels, you have a series of the very broad resonances. The width is many mega electron volts. They can overlap, and the threshold for DD reaction is about 24 MeV, corresponding to the binding energy of deuteron within helium-4. So this resonance we want to see is somewhere here in this excitation energy levels, okay? And the question is how we can argue that this resonance, additional resonance, should be here, because this energy level scheme is known for 30 years, something like this. You see here additionally a sequence of the resonances that have very clean nature or cluster nature deuteron plus deuteron scheme or structure. There is no contribution of the different clustering state, one nucleon plus helium-3 or tritons. So this resonance have a structure helium-3 plus neutron or triton plus proton, and here there are some resonances that have completely different structure, D plus D. Okay, so this is what we know, and the solution of this problem, why the people couldn't see this resonance before, is very simple. We know that the deuterons are very loosely bound nuclei, and the distance between neutron and proton is pretty large. So if you bring together deuteron and deuteron, we have a completely different distance for nuclear reactions compared to the system 1 plus 3, so helium-3 plus proton. And if you put this information, then the Coulomb barrier should be a little bit different. We should observe a double maximum structure of this Coulomb barrier, and then here at low distances, we should have a sequence of the DD resonances, this structure, and at lower distances, we have only this cluster 1 plus 3. And if you want to mix these states with these states, we should overcome this Coulomb barrier additionally. So the mixing between these states and these states is very low, and therefore we could observe this high energy excited DD levels you see here. And if we should see these resonances, we should also see this resonance and the threshold. Once again, this threshold DD at 0 plus assignment for this resonance. So these resonances are so-called P-wave resonances, similarly to the P resonances of the another clustering state. And there is a first excited state in helium-4 0 plus, and the same resonance should be for DD, placed very close to the threshold. So we have very similar sequence of this levels for different clustering states. So weak coupling is just the solution of the problem. And this something which has a very nice analogy in nuclear astrophysics. You know about this 3 alpha process, 2 helium-4, barium-8, and barium-8 is there's single particle resonance, so have a structure helium plus, helium-4 plus, so there's this single particle resonance, and then if you put additional helium-4, you can synthesize carbon-12 at higher excitation energy. And in this situation, we observe that the 0 plus state can decay to the 0 plus ground state of carbon-12 by emission of the internal pair creation electron-positron pair. 5 minutes? Oh, that's no problem, I hope. So, and this really very nice situation because this helium flash very strongly dependent on the temperature. This is something what we can observe also at for cold fusion. So once again, the 0+ state cannot decay by gamma emission because of angular momentum conservation. And we have internal production and internal electron conversion. In the case of the electron pair, or internal pair creation, we have a continuous spectrum. In the case of internal electron conversion, we have single energy line. And there is another process that can be maybe observed in the future. I don't know, we cannot say, we have no theoretical prediction about it, but this large energy 24 MeV can be transferred to the neighboring deuterons as well. So this finally we should observe 16 MeV deuterons and 8 MeV alphas. Okay, so this experimental results you have seen already presented by Rakesh, and you see that we observed for the first time electrons or positrons because the energy loss is very similar. We have very nice simulations using JANT4 packet. There's really known physics behind. You can simulate very nice different effects there. And it depends clearly on the incident energies. And then we can measure this electron counting rate compared to the proton line, and you see this increase of the ratio down to the lowest energies, and it can be described very nice using this resonance, threshold resonance that we have, and the branching ratio we have here. So the largest was is about 2, so 2 times is stronger electron-positron production compared to the proton channel. And what is, if you want to compare, you want to calculate the cross-section down to thermal energies, so you need to use this penetration factor or this enhancement factor, calculate using the screening energy, and then the resonance part that is also depending on the screening energy. The deuteron partial width is depending on the screening energy as well. So you have, in both cases, this dependence of the screening energies. Maybe there's also a very important point here, that this single particle resonance of the structure D+D change the width if we change the deuteron energy. So for high energies, we have very broad resonances, and for low energies, very narrow. And if you calculate down to the thermal energies, the cross-section for dp reaction, you'll see here the dotted line, this usual case that we include the broad resonance in helium-4. But if you take into account this new resonance we have supposed, we cannot say where is this resonance, where is the resonance energy exactly. But this resonance can enhance the cross-section, only this resonance, without any other resonances, by a factor 10 to 7, and it depends on the screening energy. So if you have a lower screening energy, close to theoretical one, we have this enhancement only factor 100, 1000, and here 10 to 7, depending on the screening energy. And as I said before, we can control the screening energy if we measure the number of defects in the crystal lattice of the targets. So, this was published just few weeks ago. And one point more, once again, similar foil slide to that Rakesh presented. This very nice experiment of Eric Ziem, University of Illinois in ICCF 24. He measured charged particles using CR39 foil at very low voltages, not kilo electron volts, but below. So the energy is really very low that measured here. And then he measured alpha particles of the energy 100 keV. But it is a coincidence that we should observe if we have pair creation, because then the recoil energy of the alpha particles should be about 80 kV. So there is a different experiment, different people, different experimental method that provides very nice argument for our theory. So finally, conclusions. So once again, electron screening effect can be locally enhanced by impurity, crystal defects, and then we observe different screening energy between 100 and 500 electron volts. We know why. That is the point. The threshold resonance can change the branching ratio, and we could observe it experimentally. We have found new reaction channels, so we should measure in the future not gammas, not maybe neutrons and protons, but electrons, high energy electrons. And the third one, so if you have this electron positron creation path, you should observe, of course, annihilation line, but the background is pretty large, so it is very difficult to observe this one. Maybe Bremsstrahlung is the solution to do it. Okay, and finally, I would like to invite all the people to ICCF 25 that should take place in Szczecin next year. Thank you very much.
Very good. I know you want to drink coffee. Is there time for questions? You have one question? Oh, no, same one guy. I mean, you should. Can you just cancel this guy?
I wish I had nothing to say. Am I right in assuming you're using zirconium in your experiments?
What does it mean?
I saw zirconium on your charts, and it was the highest peak. Are you using zirconium in your experiments?
Mm-hmm.
Yes? No? Okay, yes. All right. I want to refer you, therefore, to the 1992 patent of Mikhail Solin. Mm-hmm. All forms of nuclear transmutation, including baryon decay, in a liquid melt with an electron beam into zirconium. And it self-organizes a resonant chamber, but it's occurring in a liquid, not a lattice.
You know, there is a completely different situation. We have DD reactions. There's a completely different situation. We have DD reactions, and we measure electrons. We don't produce any electrons from the outside. You know, there's a completely different situation. There's, you know, a completely different setup. And so
okay, but all right.
Okay, any other question? Well, I think it's time for coffee break, and I thank you again, Conrad, for your talk. Very interesting. I like it. Okay, we're back here at 11:30.